Hi there. So today I'm going to talk about section 11.6. That is on comparing power functions, exponential functions, and logarithmic functions. Alrighty, so there's just a couple things that we're going to do in this section. Alrighty, 11.6. So we are comparing power functions, exponential functions, and log functions. Recall, power functions have the form k times x to the power of p. Exponential functions have the form a times b to the power of x. And logarithmic functions have the form log of x. Okay? People tend not to confuse log functions with either of the above, but what I would like to say, just so that you're clear with the difference between power functions and exponential functions. A power function has x as its base and a set exponent, whereas an exponential function has a set base and x is the exponent. So I think the one way you can look at this is a power function. This is an exponential function. Okay? Notice your base here is x, whereas with the exponential function, your exponent is the variable x. Okay? So what I'm going to do is I'm going to make some generalities here, general statements. We're going to compare some graphs, and then we're going to solve a few different questions. Okay? Essentially, what I would like to say about your power functions is the larger the value of x, the faster it climbs. Okay? And higher powers dominate. Now, that is the case when x obviously is greater than 1. If x is between 0 and 1, so for example, then you're looking at, say, 1/2 raised to some power versus 1/3 raised to some power, okay? Then the smaller power dominates. Again, because here, if you take, say, 1/2 to the 4th power, you're going to get 1/16. Whereas 1/3 to the 4th power, you're going to get 1/81. Clearly, that is much larger. Okay? Now, for our exponential functions, what I would like to say is as follows. And again, you can read this stuff in your book to get more of the details. Right now, for just the comparisons, I'm just outlining them. Okay? So for the exponential functions, any positive increasing exponential function eventually grows faster than any power function does. So while power functions might initially grow very quickly, ultimately, as long as you have an increasing exponential function, eventually, as your x values get large enough, the exponential function will grow much faster. Okay? Now, in the same sense, dealing with our exponential functions, any positive decreasing exponential function will approach 0 faster than any decreasing power function does. And what I would like to say about the log function is this is the slowest grower of the three types of functions. So ultimately, your exponential functions grow the fastest, then your power functions, then your logarithmic functions. Okay, so having said that, what I would like us to do is as follows. Let's look at this example here. Okay? What I want us to do, again, you guys can look at a lot of this stuff in the book, that's very clear, but I'd like to work out some actual examples with you. And what I want us to do is find a possible formula for f if f is, part A, we're going to pretend he's a linear function. Part B, we're going to pretend he's an exponential function. And finally, for part C, a power function. And let us say for this first example, we have f of 1 is 18, and f of 3 is 1,458. Okay? So, what I want us to do here is find the formula if each of these ordered pairs are representing either first a linear, then an exponential, and then a power function. Okay? This is a really nice last section of the course because it really asks us to bring a whole bunch of things together. Okay? For example, let's go back to if f is linear. Recall, if you have a linear function, it's of the form y equals mx plus b. Okay? Well, in order to find the equation of the line, at the very least, we need two ordered pairs. And I claim we are given two ordered pairs. One ordered pair is 1, 18, and the other one is 3, 1,458. All right. Now, when we want to find the equation of a line, and we're given 2 points, first thing we need to do is find the slope. Recall, the slope of the line is the change in y values over the change in x values. So, if we do this, of course, we get 1,440 divided by 2. So our slope is 720. Wow. That's pretty steep slope. All right, so at this point, we have y is 720x plus b. In order to find the equation of our line, we need to know what b is. Now, we can either use that y minus y1 equals m times x minus x1, or we could use y equals mx plus b. Okay, since we have the y equals mx plus b right here, let's just use that. How do we do that? Well, what we do is we plug in either one of these ordered pairs in for x and y, and then solve for b. I'll plug in my top ordered pair. We know y is 18 when x is equal to 1. So I get 18 is 720 plus b. Solve for b by subtracting 720, and we're going to get negative 702. So, I can say now that if this ordered pair, set of ordered pairs represented a linear function, my function looks like this, 720x minus 702. All right, that was that. Now, if this is an exponential function, Recall that's equal to some number times b to the power of x. Now, you may or may not recall this, but when you're given an ordered pair with a 1 comma some number, we're actually in a bit of luck. Okay? So, how can we do this? Well, recall one way that we looked at these things is we looked at the ratios. Okay? This is the general way that we saw that this worked. Our y value, 1458, is equal to a times b cubed. And now I can plug in my other ordered pair. Y is a times b to the first power. All right. Remember we looked at the ratio of these? Our a's cancel. B cubed over b is b squared. And 1,458 divided by 18 is equal to 81. Sweet. Okay, we don't want b squared, we want b. How do you get rid of squaring something? You take the square root of both sides. And yes, the square root of 81 is positive or negative 9, but we always want to consider a positive base, so we get b to be 9. So at this point, we have y is equal to a times 9 to the power of x. Now, just like with our line, we plug in one of the ordered pairs to solve for the other unknown. I'm going to take the smaller ordered pair for obvious reasons. So y is equal to 18 when x is 1. So we're solving 9a equals 18. So a is equal to 2. So if this is an exponential function, we have 2 times 9 to the x power. All right, one last guy to deal with, and that is if we have a power function. Recall a power function is k times x to the power of p. Okay, I think you'll grant me that I could say 18 is k times 1 to the power of p. Why did I just plug that in? Because we just covered our power functions very recently, and we saw that if you have a base of 1, plug it in, precisely because your y value is what your k is. So already I have 18 times x to the power of p. Now what I'll do is I'll plug in my other ordered pair. I know that y is 1,458 equals 18 times 3 to the power of p. Alrighty, so we need to know what is p. First thing that we're going to do is isolate our exponential. We'll divide both sides by 18. Fortunately, we've already done this operation. I have 81 is 3 to the p. Now, you might know that 3 to the 4th power is 81. Let's pretend you didn't know that. Okay? When you're solving something like this and you want to get your exponent, that is when we use our logs. Okay? We can take the log or the natural log of both sides. You might ask, wait a minute, why do we do that? Again, because when you have the log of something raised to a power, you can bring your exponent down in front. Now, to get p all by its lonesome, we'll divide both sides by the natural log of 3. And you will see that the natural log of 81 divided by the natural log of 3 is equal to 4. So, if this guy was a power function, we would have 18x to the 4th power. All right, so Let us do this one more time. But now what we're going to do is we're going to start out with f of 1 is 16 and f of 2 is 128. And let's now find the formulas if we first view this as a linear function, then an exponential, and then a power function. All right, so part A, if this is a linear function, we have y equals mx plus b. In order to find the formula for this function, the first thing we need to do is find the slope. Well, the slope is the change in the y values over the change in the x values. What is 128 minus 16? 112, and 2 minus 1 is 1. So we already have y equals 112x plus b. Now what I'm going to do is take one of my ordered pairs and I will plug that in. I will take my top ordered pair. I'll say that 16 is 112 times 1 plus b. All right, well, there's not much to compute here. The only thing we have to do is subtract 112 from both sides, and you're going to get b to be negative 96. So, our formula here is 112x minus 96. And that is the equation for my line that passes through those 2 points. Now let's find the equation of our exponential function that passes through these exact 2 same points. Recall an exponential function is of the form y equals a times b to the x. And let's plug in both of our ordered pairs. I have 128 is a times b squared. And I have 16 equals a times b to the first power. We can look at the ratios of these, and 128 divided by 16 is equal to 8. Our a's cancel, and b squared over b is simply b. So we already have y equals a times 8 to the power of x. Now what we need to do is find our value of a. Again, we can plug in either ordered pair we want. Again, I'll plug in my top one precisely because it's less work. I have 16 is a times 8 to the first power. Well, 8 to the first is 8. We can divide both sides by 8 and we'll get a to be equal to 2. So if this is an exponential function, we're going to get 2 times 8 to the power of x. Last but not least, let us do this if we have a power function. Okay. Again, if we have a power function and we see that one of our ordered pairs has x equal to 1, we know that our y value actually gives us the value of k. If you didn't recognize that, again, with a power function, you have k times x to the p. You can form the ratios just like we did with our exponential function, right? You could say 128 is equal to k times 2 to the p power. And then you could say 16 is equal to k times 1 to the p power. Now, you can form the ratio and go through all of that if you would like to. Again, notice this bottom equation tells us already, hey, k is equal to 16. Okay? But again, suppose you weren't paying attention to that. You would form the ratio. 128 over 16 we know is 8. K over k goes bye-bye. And we have 2 to the p over 1 to the p. Recall, we can write that as 2 over 1 to the p, but that's 2 to the p. Okay? Now, Again, you probably know that 2 cubed is equal to 8, but suppose you didn't pay attention to that. You could take the log of both sides. You could say the natural log of 8 is the natural log of 2 to the power of p. You always take the log when you're solving for your exponent, precisely because you can bring your exponent down in front. We can divide both sides by the natural log of 2, and you will see that p is equal to 3. So assuming you didn't even recognize yet about the k being our constant value here, we've already gotten that p is 3. Now you can take either ordered pair and plug it in. So you could say 16 is k times 1 cubed, but 1 cubed is 1, and you're still going to get k to be that same value. Did I work harder to solve this? Yes, but I wanted to show you that even if you didn't recognize with the ordered pair 1 comma what have you, that would give you your value of k, you can still get there. So we have 16x cubed. All right, that completes section 11.6, and not only does that complete section 11.6, that completes all the videos for this class. So I hope you found them to be very helpful. I certainly had a ball making them. Thank you.